Okay, for this training assessment, this is our second installment. So you can say it's 2B. There's no 1B, it's just starting off at 2. So it says we're going to understand the graph of an equation in two variables is a set of all its solution. And then it says I can graph exponential functions showing the x and y intercepts and end behavior. So this right here is all of this part. So you can graph using your knowledge of the x and y intercepts, but more specifically about the domain and range, and that you really understand what the graph is doing. The first standard, the AREI D10, you're understanding the graph is the set of all solutions. It's just, can you graph the ordered pairs? So in this problem, we have the y equals 3 times the quantity 0.5 raised to the x power. So you can, if you don't have a graphing calculator at home, you can use desmos.com. So it's 3 times 0.5 caret x. So you're going to get a decay model, Control T for the table. Now the table that is given goes from -3 to 3. And we just made that table just so you could have a larger reference of all the numbers. If we don't give you the x values to plug in, then just do any x's. So copy that down. You got 24, sorry. You have 24, 12, 6, 3, 1.5, 0.75, and then 0.375. Now on your graph, if you can't plot 24, that's no big deal. You can use that as a way to lead, and I'll explain what that means in a second. -2, 12, so left 2, up 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so did that point, -1, 6, 1, 2, 3, 4, 5, 6. Did that point 0, 3, which is your y-intercept, which you can find as your a value. It's your initial value. 1, 1.5, so you're going to go up 1 and then another half. And then 2, 0.75. So almost a 1, but not there yet. And then this is below the halfway point. Now what we as teachers are looking for is that you know that the graph has an asymptote, which means it's not crossing the x-axis. It's always trying to reach it. And then that it curves. So it kind of looks like the heel of your foot. So that's what we're really looking for. And now I understand that you can't plot -3, 24, but this arrow should lead to where 24 is on the graph. So you just don't want to do a straight line, which I've seen. So you don't want to just do a linear line up there. That would be incorrect. Now, it says describe the domain of your graph. So domain is a vocabulary word, which is the x values. Now, when it says describe the domain, you're looking for any of the x's that will work. Now, if you keep the calculator and you look right here, I can hit the up arrow forever, and it's getting more and more negative. So if I just do it for like 3 seconds, I'm already at -32. It's never going to stop. So since our graph never stops to the left, that's -infinity. Now, if we want our x's to get bigger and bigger and bigger, I can scroll down And I can do this for as many seconds as you want me to. And the graph is never going to stop. So since it never stops to the right, our domain is going towards positive infinity. Now our range value is our y. So this is our y values. So right here, our graph will never go into the negative y's. It's just impossible. So what is our graph trying to sit on? What is our graph trying to reach? It's trying to reach 0. That is the lowest value that it's trying to get to. Now, what is the highest value that our graph is trying to get to? Infinity, because our graph is always going up, 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 up. It will never stop. So our y values is showing us that it's going to a positive infinity. Now here it says describe the decay factor. So you want to look back at your equation that I gave you. Our decay value is the base of our exponent. So this is decay because it is between 0 and 1. So for it to be a decay, our b value has to be between the value of 0 and the value of 1. So you can say it's decreasing or decaying by a factor of 0.5. We know that because that's the number shown. Another way you can check is on the table. If you multiply 24 times 0.5, you're going to get 12. If you're going to multiply that by 0.5, you're going to get 6. You multiply 6 by 0.5, you're going to get 3. And you can do that pattern for the entire table. Now your y-intercept, you can locate 3 different spots. It could be the 3. It can be on the table, 0, comma, whatever. And it's also on your graph. So since it's an ordered pair, it's 0, comma, 3. Initial value, same thing as y-intercept. Those are going to be the same value. Now, the part that students really struggle with is end behavior. So this is the behavior of your graph at the end. Now, our graphs usually don't end, so it's challenging for students to realize this. So as x is getting bigger and bigger, so if I added 4, the next value would be 0.1875. If I got bigger at 5, my value for my y would be. So you need to ask yourself, what's happening to our numbers? Our numbers are decreasing. Which number is it trying to get to? And that answer is 0. Now, as x is getting more and more negative, so if I just go to the table, go negative, it goes to 48, goes to 96, 192. It's going higher and higher. It's trying to reach infinity. Now you're going to do the same thing for number 2. So for number 2, you're going to add graphs. So this right now is 0.5 times 3 raised to the x power. So that looks like a growth problem to me. 0.5 times 3 to the x. So then you just copy the table down. So So we're going to start off with very small numbers, which is fine. Eventually we'll get to better numbers or easier graphing numbers. Okay. So from here, we go -3, and we barely go up because it's 0.019. So there we go. And then that's like the halfway point. Oh, I'm sorry, it's like 5 pennies. Then it's a little bit more up. And then 0.5 is right there. 1, 1.5 is right there. And 1, 2, 3, 4.5. And then 13.5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13.5. Okay. So this part right here is hard to graph, but as long as you don't go underneath the x-axis and you have that curve shape, and we know that it's not a linear, you'll be fine. Now the domain, your graph is always going to the left. It's always going to the right, so that means -infinity to infinity. What number is our graph trying to sit on? It's trying to sit on 0. It's trying to reach 0. And then if you look higher up, what is it trying to reach? It's trying to reach positive infinity. Now the growth factor, the graph is increasing by a factor of 3. How you get that information? There's a 3 here. It's the base of the x. If you multiply this number, if I did not round it, by 3, you would get that number. Multiply this by 3, you would get this number. Multiply this by 3, you would get a half. A half times 3 would get you 1.5. 1.5 times 3 would get you 4.5, so on and so forth. Now the y-intercept. In this equation, it is our initial value. I apologize, you need to write that as an ordered pair. You can find the y-intercept on the table or the graph. Your initial value is the same as your y-intercept. Now, as x approaches positive infinity, our y, as it's going to the right, what is our y doing? It's going up. So it's positive infinity. As our x's is going to the left, what is our y doing? It's trying to reach 0. It's trying to sit on 0. Now, number 3, 4, 5, and 6, those are notes that we did not finish today, but they'll be finished. So if you're struggling with 3 through 6, that's okay. It's just the beginning. It says in 1983, the population of Detroit was 120,450 people. Since then, the population has decreased by about 1.2%. Find the population in 2001. So here, our x is our time in years, and our y is our population of Detroit. Now our given. What I recommend you doing, we need to find the information to make this equation okay. So our a is our initial value. It's our starting value. So the value that we're talking about in the beginning is 120 26,450. Now the B value, this is the complicated part that we started notes on. You want to look at the decreasing and then the percentage. So decreasing by 100 or by 1.2%. Now, since we're decreasing, we want to use the exponential decay model. So that says 1 minus r. That's our B value. 1 minus r. Now, the trick for this is to find the r value. And we need to use the percentage to help us with that. So to find the r, you do a 1.2% divided by 100. And you're going to get that decimal. That decimal is what you plug into r. Once you do that, then you go to your calculator. It doesn't matter what calculator you have. You do 1 minus 0.012, and then you get the decimal. So you're 0.988. This is your B value. You have to do all of that work to get your B value. So we found our A value, we found our B value, now we have to find our X value. Our X value is the time. So we're looking for the population in 2001. However, we need the 1983 to start with. So we need to figure out how much time went by, and you do that by subtraction. So 18 years. So that's going to be our X value. So our unknown is our Y value. It's the population. Now our equation is y equals a times b raised to the x power. So y equals 120,450 parentheses 0.988 raised to the x power. But we're looking for 2001. So we know 18 years went by, so we have to plug that value in. Now, in any calculator, it doesn't need to be the calculator that we have. You just plug that in exactly how you do it, or how you see it. So it is 120,450 times 0.988 raised to the 18th power. And then you get 96,924.1. Now we are talking about population, so this part right here, we can't have decimals. So since it's 0.1, we're just going to drop it off, and then this is our whole number that we're going to do. So the population in 2001 is about 96,924. Now for number 4, it's going to be very similar to that. So you just want to make sure that you know, and the only difference between these problems are decreasing and increasing. So for number 4, it says, since 1927, the daily cost of patient care in hospitals in the U.S. has increased about by about 2.7% each year. In 1927, such hospital costs were on average $560 a day. So what is the approximate cost in 2002? So you want to define your variables. Your x will always be time. And in this case, we're talking about years. And then what is our overall y talking about? It's the hospital cost. Now, just like number 3, we're going to rewrite our a times b raised to the x power. Our a value is our starting. So since we care about 1927, we want to know the starting value of those daily costs, and that was $560. Our b value, this is our new part. It says that it increased. So we want to look at our notes, and we're talking about growth. So our b value can be represented as 1 plus r. So how much did it increase? It increased by 2.7. But since it has that 2.7% to it, we need to divide by 100 to get rid of that percent symbol. So when you divide by 100, it's 0.027. This is your r value. So you need to plug it into that value. So then we add that decimal to 1, and you get your b to be 1.027. So far, we have our a value, we have our b value, and since we're evaluating, we're going to need our x value. We care about the cost in 2002, and you need to look at the year we started, which is 1927. So to figure out how many years went by, you need to subtract the 2. So 75. Now for the unknown is the challenging part, because you want to look back in the problem, and it's what is the cost in 2002? And since we talked about costs for our y, that's why we're solving for our y. So costs in 2002. So we rewrite our generic equation. Y equals a times b to the x power. And then you just fill in all the missing pieces that you already did in the given. Now, since we care about the cost in 2002, we're going to write a 75 in place of x, because that's 75 years after 1927. So in your calculator, you're going to enter this information. So we started at $560. Our growth was 1.027. And that was raised to the 75th power. So then you get about $4,130.20. Notice my calculator just said 0.2. Since there's no number, that really means 0.20, which is to the nearest penny because we're talking about money. So the cost in 2002 would be about $4,130.20. Okay. Now, number 5 and number 6, I recommend you just hitting pause for my video and you trying it out on your own, and then hitting start or hitting play once you have the problem, and then you can go and see if you did it correctly. Because number 5 and number 6 are just like number 3 and number 4. So hit pause now, try it on your own, and then go back to it to check your answer. So it says the number of student athletes at Fordson is 520 and increasing at a rate of 2% each year. Write an exponential function to model this situation. Then find the number of student athletes after 5 years. So X, we're talking about time again. Once again, we're talking about years. And then our Y is the number of student athletes. So our A value they gave us was 520. That's our starting value. Now our B value, it says increasing. So you want to look back on your notes, and our increasing is the 1 plus R because it's growing. So you want to do the 1 plus R. But I don't give you the rate, I give you the percentage. So we have to change that percentage. To change the percentage, we divide by 100. And once you do that, that is your rate. Then you plug that in. So 1 plus 0.02. So your B value is 1.02. So now we have our A value. Now we have our B value. What we need to find is our X. Problem number 5 is actually simpler or more easy than the previous two problems because I gave you after 5 years. So you don't have to do any math. You just write 5 years. The unknown is number of athletes. And then our equation is set up as y equals a times b raised to the x power. Where a, we talked about 520 students. B is growing, so it's 1.02. And then raised to the x. But since I care about 5 years from now, instead of x, we're going to put 5. That part you're going to put into the calculator, this whole thing. I recommend doing it all at once. If you don't do it all at once, you have to do the order of operations. Once you do, so you're going to put 520 students times the B value, the growth value. So 1.02 after 5 years. So you're going to get about 574 students. Now notice that we're talking about people. So this decimal, we're not going to use. So you can say in 5 years, there will be about 574 athletes. All right, for number 6, it says Ali buys a Fordson tractor for $47,000 if the tractor depreciates. So that's a new vocab word. Depreciates means decline or decrease. 3% each year. Write an exponential unit to find the value of the tractor after 10 years. So the x is still time. it is still years. Our Y value is the value of the tractor. So when I find the X and Y, you're really just looking for what are the two main ideas, what are we talking about? And then for our given, we have Y equals A times B raised to the X power. Our A value is our starting value. We know that Ali bought the tractor for $47,000, so that's our beginning value. Now, since we use the word depreciate, which means decline, decrease, you want to look and see, since we're talking about decreasing, it's decay. So we have to do the 1 minus R. But once again, we only have the percentage. We can't work with the percentage. So we have 3%. We have to divide by 100 to get rid of that percent sign. And when we do, it's 0.03, and that is the rate value. Since we're declining, we have to minus. So 1 minus 0.03 is 0.97. And then our X value, they tell us after 10 years. So we lucked out. It's less work for us. So we have our A value, we have our B value, we have our X value. Now, our Y is the value of the tractor. So once again, we use the equation Y equals A times B raised to the X power. And everything that we have highlighted, we plug in. So we have the 47 grand times the 0.97 raised to the X, because that's our equation. And then we can plug in the 10. So 47 times 0.97 raised to the 10. Let's see what that gets us. When you're doing this, you want to make sure that you are putting it right in the calculator. So make sure there's 3 zeros at the end. The 0.97 raised to the 10 power. So that will get you about $34,658.90. So notice that my value 10 years later is a smaller value than my A. That's one way you know that you are doing it correctly, because we said that the value is decreasing. So your answer should be smaller than your initial value. So the value of the tractor will be about $34,658.90 in 10 years.